Good morning and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about capacitors and capacitance. This is in some books sort of its own topic. So some textbooks will break capacitors, capacitance, dielectrics, and all that into one chapter that is separate from the chapter on electric potential. Others combine it into the same chapter. So for what it's worth. So what is a capacitor? Basically what a capacitor is it's typically a pair of conductors which are oppositely though equal magnitude charged. So you might have one conductor here with charge plus Q and then another conductor over here with charge minus Q. Okay, so this will create a capacitor. Among other things, you'll end up getting some sort of an electric field that runs from the one to the other. This actually, looking forward, is how these, or is one way that you could say that these store energy was within this electric field. Although when I do the section on energy for the first time, I'm just going to talk about it in the context of stored charge and voltage drop. Now, the fundamental property, I guess you could say, of a capacitor is capacitance. And so capacitance has SI unit farad, or MKS unit is farad. F. It's defined, the capacitance is defined by how much magnitude of charge is being stored on these two conductors per unit voltage drop between them. All right, so that is our actual definition for capacitance. It's not necessarily how we want to go about finding capacitance. It is if you happen to know what the charge is and what the voltage drop is, then that gets you capacitance. But it's kind of like in a previous lecture when we said that the wave speed v was equal to the wavelength lambda times f. So this was propagation speed. And then I kind of continued by figuring out what actually determines the wave speed for a given scenario. And it's not really wavelength or frequency. Typically, you figure out what your wave speed is from other properties. So for example, this could be determined from or predicted from, let's say, V equals square root force of tension divided by mass per unit length. Okay, so you could get the tension force at equilibrium for a string. You could figure out what the string's linear mass density is. If you divide the two by each other and take a square root, then that tells you what the speed should be. Or for speed of sound in air, or in other three-dimensional media, you have your bulk modulus divided by your density. Or we also had the one that was V is V naught square root T over T naught. So this was sound actually in air or any other gas as a function of temperature. So notice that none of those equations make use of lambda nor of f. They don't make use of the wavelength or the frequency. So why is that? Well, on a wave on a string, let's say that you're trying to build a standing wave at resonance, and so you start plucking one end of the string or driving one end of the string, and you find a resonance, and that's great. And then you change the frequency and find another resonance. That's great, and you can measure the wavelength by counting antinodes on the string. The thing is that what you'll find is that as you increase that frequency to get more and more waves per second sent down the string, you actually decrease the wavelength or the distance between the waves. All right, so we will work a quick example. We want to determine the capacitance for a pair of conductors which stores 32 millicoulombs magnitude on each of the two when there's a potential difference of 40 volts. So capacitance is defined by charge divided by voltage drop for the pair. Defined by can also mean equals, so we can just write an equals sign here. So Q is 32 millicoulombs, and delta V is 40 volts. We can either convert the units or make use of the fact that a coulomb per volt is a farad, and therefore a millicoulomb per volt is a millifarad. 32 over 40 in any case is 0.8, and so the answer is 0.8 millifarads, or if you converted your units and wanted to put it out in farads, it'd be 8 times 10 to the minus 4 farads. For waves on a string, if I have a driver that is driving this end up and down, maybe my actual node is here, and I have a fixed end here. For example, the string is running over a pulley or something. Then what I will actually end up with is, for one frequency, I'll end up with a wave like this. So this is like my second harmonic. And then for some other frequency, I might end up with a wave like this. And so this is a higher frequency wave. I'm kind of exaggerating how much this might be, but notice that this right here, this is lambda over 2, is this is a lambda between the two peaks. But what I end up actually getting is that my nodes and antinodes actually form something that looks like this. Whoops, I've already kind of messed up my drawing. Comes down here, comes up here, comes down here, comes up here. And so I have some areas at which it's either very high, very low, or somewhere in between, other areas where it doesn't move. And so this distance between two consecutive peaks on the original, but between 1 to 3 peaks on the standing wave, that's your lambda. And notice that that lambda is somewhat smaller than the wavelength that I get for this wave right here. This right here is lambda for the sort of a first order wave, or the second harmonic wave as it is. Second harmonic wave, first overtone. What that basically means is that as my frequency is increased, my wavelength decreases so that I have the same value of V. Now, why I brought all this up is because if I come back here for my capacitor, basically if I connect to a battery and apply some voltage between the two, I'm going to get some charge. If I connect to a stronger battery with a higher voltage, I'm going to also get more charge. And in both cases, I expect to see the same capacitance value as long as I haven't actually changed anything about the two conductors themselves. So the question maybe should arise, what is it that actually determines the capacitance for the system, in the same way as we might have asked what actually determines the wave speed for this string? And again, I could calculate a capacitance. If I have, say, 2 coulombs being stored for 4 volts, then my capacitance is 2 over 4.5 farads. That's actually a very high capacitance, by the way. And so in order to answer the what is actually going to determine the capacitance question, we have to know what kind of geometry we're using, because the answer is very geometry dependent. Now, in an algebra-based physics course, the only real geometry that we ever deal with is a pair of parallel plates. So I have plate number 1 over here. This one is the positively charged, let's say plus Q. I have plate number 2 over here. This one is my negatively charged plate. And they are separated by some distance. So this distance between the two plates we'll call D, and each plate has area A. So now we ask, what is the capacitance for this configuration? Well, we know that the electric field should look something like this. It should just be a set of parallel lines between the two plates. And those parallel lines are determined by what? I'll let you think about that while I'm drawing the lines. You should be able to answer it from Gauss's law, but you can get the electric field strength. So here's E. Recall that E is equal to, for a single plate, it would be sigma divided by 2 epsilon naught. For the pair of plates in here, it's actually sigma divided by epsilon naught, or in other words, charge per unit area times epsilon naught. Okay, so that's your E field strength. Now recall that the magnitude of delta V would be the magnitude of E times the distance. Okay, so that means that my delta V is equal to Q times D divided by A times epsilon naught. Now we ask, what is the capacitance? Well, using capacitance is defined as Q over delta V. What I end up getting is Q divided by Q times D over A times epsilon naught. Now I can cancel the two Q's, so notice that Q has dropped out of here. And what I'm left with is that C is equal to epsilon naught times A over D. So this is the equation for a pair of parallel plates. So let's call this capacitance for parallel plates, where again A is plate area for each plate, D is distance, and epsilon naught is that familiar permittivity of free space, which is 8.854 times 10 to the minus 12, although now we can write it in new, more convenient units. We could write it in terms of farads per meter rather than the old coulomb squared per Newton meters squared. So we have a more convenient unit now for epsilon naught. Incidentally, that means that the unit for Coulomb's constant is validly meters per farad. Much easier to write than the longer unit. Okay, let's do another quick example at this point. We've just determined that the capacitance is epsilon naught A over D for a pair of parallel plates. Now we're given the set of parallel plates and told that each one has an area of 600 millimeters squared and that they're separated by a distance of 12 microns or micrometers. So the capacitance for the pair of parallel plates is epsilon naught A divided by D, area divided by distance. That is 8.854 times 10 to the minus 12 farads per meter times an area of 6 by 10 to the 2 millimeters squared, except for that you need to convert the millimeters squared to meters squared. So 1,000 millimeters per meter by another 1,000 millimeters per meter. So we're looking at 10 to the minus 6 square meters per square millimeter. And then all of that is being divided by that distance, which is 12 microns at a rate of 10 to the minus 6 meters per micrometer. So our 10 to the minus 6's cancel here. 6 divided by 12 obviously is 0.5. So I have 0.5 times 10 to the 2 times 10 to the minus 12 times 8.854. So that should give me 4.427 times 10 to the minus 10 farads. And then probably we should round it to 2 sig figs since there's only 2 here. So C is about 4.4 times 10 to the negative 10 farads, or in other words, 0.44 nanofarads. And so that's our answer for this particular pair of parallel plates. So that is capacitance for, in general, the definition, and for a pair of parallel plates. We can also, in principle, do capacitance for other geometries, but we can't really derive it without making use of calculus. So here's a set of different geometries. The parallel plates basically means that you have one here and you have one here, and each one has an area A. They're separated by distance D. The capacitance again is C equals A over D times epsilon naught. Concentric cylinders basically means that you have one cylinder right here and then another cylinder kind of surrounding it, and they should be actually centered at the same location. Kind of hard for me to draw in real time. And then from the side, you basically have a cylinder and you basically have a cylinder. Like so. So for this geometry, you need to have a radius for the inner. We could call that R inner. And we need a radius for the outer. We could call that R out. And so the capacitance for this pair, C is equal to, as it turns out, 2 pi epsilon naught. Oh, and also this has a length L. 2 pi epsilon naught L divided by natural log of the inner and outer radii. For the concentric spheres, you basically just have one sphere inside of the other, or embedded in the other, and you get 4 pi epsilon naught times the product divided by the difference in radii. All right, so that is the geometric determination of capacitance for 3 geometries. And that's all that I'm going to cover in today's video, so thanks for watching.